Okay. Hello, everyone. And this is a technical walkthrough call with Ethereum testing team. We're here joined by Dan and Spencer. Gentlemen, thank you so much for joining this call. For everyone who will be watching this in the recording, this is a part of the technical walkthrough series that we're, as Immunefi team, recording together with all Ethereum projects which are participating in the Ethereum Attackathon, which is currently live on the website. It went live on November 25th, as yesterday on the day of this recording, but it's still live by the time that this goes on our YouTube. It's going to be live till January 20th with the rewards of up to $1.5 million. But we're not here to advertise it. Dan, Spencer are responsible for testing here on the Ethereum, and they're here to share the knowledge and valuable information. So guys, please take it away, and thank you so much for joining once again.
Sure, thank you. I'll just share my screen now, if that's okay.
Absolutely.
Okay, am I sharing? Perfect.
Yes, can see it very clear.
Okay. So yeah, thank you for organizing this. I think it's such a great initiative to get, I guess, security researchers involved and find more bugs in Ethereum, because I'm sure there's one or many that we don't know about. So yeah, thank you. So today we're going to go over Execution Spec Tests, which is the main repository that myself and Dan and the rest of the Ethereum Foundation testing team predominantly work on, with the context of the Immunefi hackathon. Now, just a quick disclaimer. So the aim of our repo is not to find bugs within it. So if you find bugs within our repo, you won't get paid. But if you do find bugs within our repo, when you use it, if you use it, please report them on GitHub just as an issue. But yeah, the purpose of our repo is to use the tools that we have to help you find bugs or consolidate on bugs that you've found already within the execution layer clients. And specifically, this repo is for testing the execution layer, just to avoid any confusion.
This is a wonderful remark, honestly, Spencer. Thank you so much for mentioning it. Yeah, guys, for everyone who's watching, for all whiteheads and security researchers, the scope of the Attackathon is live on the page. And if you don't see the mentioned repository in there, just don't use it. So very good remark. Thank you, Spencer.
No, thank you. So as I said previously, it's myself and Dan that work on the repository, and then also two others, Mario and Dimitri. And if you have any issues at all, if you choose to use it, please get in touch with us. We're more than happy to help. Okay, so what is Execution Spec Tests, or EEST? So essentially, it's a custom Python framework that helps us do three things. So the first thing is write execution layer tests in a readable Python format. So previously, a couple of years ago, tests were written in YAML, in Ethereum tests, in a format which is hard to read, especially with a forever growing complex Ethereum. So now we have this Python format which we can write tests in, very readable and very parameterizable. The second point is generating the actual test fixtures that can be consumed by the clients. So with the test production kind of process, first you'd write the test in Python and then generate it into a JSON fixture which can be consumed by clients. Again, previously with Ethereum tests, this was done with another tool called retest.eth, and previously maintained by Dimitri, who's on our team. And the reason it differed before was retest.eth was in one repo written in C++, and Ethereum test was in another with the YAML tests. Retest ETH would be used to generate JSON fixtures using the YAML tests. But now with the execution spec tests, we have the Python tests in one repo and the generation of the test fixtures in one repo. So it's brought everything together. And the third thing, finally, is actually running the tests against an execution layer client. So these three things together make test development and I guess debugging a lot simpler than it used to be. And just to highlight, we are still a fairly new repository. We've kind of only been involved in the development process for maybe the past 2 years. Okay, so the aims of execution spec tests. So from our side, our main aim is to provide the source of truth for client implementations in the form of our tests. The way I like to think about it at a high level is essentially we write tests based on EIP specifications, and then the clients consume those tests. And if our test and the clients that consume, if the client passes our test, they're in agreement with the spec, our understanding of the spec to write the test and their implementation of the spec. Now, when you add multiple clients, assuming all clients are passing the tests, we're all in agreement with our understanding of the spec. And as you know, with multiple execution layer clients, things can get confusing. And also with EIPs and written text, it's hard to understand sometimes the spec clearly. So I guess our main aim, especially during the development lifecycle of the execution layer, is to kind of provide this source of truth for clients so that during development, when a new EIP is added, clients are kind of all in agreement with what the EIP does. And yeah, so our tests right now are used on mainnet and yeah, testing the development forks. So Prague, which is upcoming, EOF and Verkle, we have tests for too. And yeah, our second kind of aim is just to improve the development lifecycle for execution layer clients. So we kind of want to make it extremely easy for clients to start writing the spec for EIPs. So we recently started working with another team called EEST, who maintain the Ethereum execution layer specs. And essentially what they've done is, for all of Ethereum, they've written it in a very clear Python specification. And as developers, we understand code more than written text, and text can be very verbose and ambiguous. So EEST fits the gap there. And with EEST, we now use them to generate our test fixtures. And with the generated test fixtures from EEST, assuming EEST implement the spec before other clients, we can have tests before clients have even started implementing new changes. So when I say improve the EL client development lifecycle, I mean have tests ready before clients even start implementing. So this is something we really want to do in the future. And on top of execution spec tests, we create and maintain external test tooling. So there's one other repository that we work with highly called Hive. If you're familiar with testing in Ethereum, I'm sure you've heard about it. It wasn't created by us, but we certainly use it, and I know a lot of other teams that use it too. And I guess a final aim here, just to mention Ethereum tests, we aim to replace it and deprecate it by the end of 2025. And to do that, we need to port all the existing tests from Ethereum tests over into our repo. And after that, execution spec tests will be the main source for tests. It's also worth mentioning that for new tests, for development tests, we are the source, but for, I guess, Shanghai onwards, Ethereum test was I guess the status quo. Now, just to give you the aim of EEST with Immunefi and the hackathon. So what can you use EEST for the hackathon? So if you find a bug using some other method, you can use Execution Spec Tests to write a test to help you validate the bug, and additionally use that test within a bug report. The second point, you could use the repo to write really complex test cases to catch consensus bugs, which is possible. If you know the ins and outs of Ethereum, it's very possible to do that with our repo. But the main thing, in my opinion, which stands out is if you find a bug and you want to write a test for it, it makes so much sense to write it in our repository, because with one test, you can test every single client for that bug. Okay, so framework overview. So today, I won't go into everything that our repo does, but predominantly go over how to write a test in Python, fill it with the fill command, so generating the test fixtures from the Python test that we write, and then consuming the generated test fixture against the client. And yeah, not covered today is these two plugins or commands, execute and gentest. Now, execute is very useful for us, but in the context of the hackathon, I don't think it's super useful. Essentially, if you write a test in Python, it lets you use the existing Python test transactions and send them to a live network. So it's great for devnets, but if you're trying to test on mainnet, you're going to be spending a lot of ETH. Unless you set up your own devnet, it's possible to use. More on that later. And then also gentest, which isn't working yet, or fully working yet. It is working. Essentially, given a transaction hash from mainnet, gentest will use that transaction hash to derive a Python test and actually create a Python test for you based on the transaction hash. So if there's already a bug that exists, if you have the transaction hash, you can use gentest to generate the Python test. Essentially, the reason I've marked soon here and I'm not covering it is because it only works for, I believe, 1 or 2 transaction types, not all of them yet. So that's still a work in progress. Okay, so I'll go over fill now. So essentially, when you write a test, you're writing it in Python here. And it's great that you've written the test in Python, but clients can't do anything with that. So in order for clients to actually use the test, we have to use a reference EVM to fill the test using their transition tool. Now, I mentioned earlier we use EELS, Ethereum Execution Layer Specs, as our new reference EVM to fill tests. So assuming the item of the test you want to, or what you want to test is in EELS, or the spec is already implemented in the EELS reference EVM, then you can generate the test for Python, or for the client. Okay, yeah, I guess now I will show you kind of live how it works. This diagram will make more sense if I show. Let me just make my screen a bit bigger. So I've already defined a basic simple test, just called test simple here. And when you write a test, you mark it with a PyTest parameter. You mark it with PyTest, with this valid from marker. And here we've marked it valid from Cancun. So essentially, when we run fill on this test, it will only fill it from Cancun. If we marked it valid from Shanghai, it would fill the test for Shanghai and also Cancun. So here we've defined the test as a state test. So it's worth mentioning we have 2 main test formats, so a blockchain test and a state test, but we'll focus on state tests for now. And we have some pre-allocation. So within a test, there are, I guess, 3 main components. You have the pre-state, or the state of the world before any excitements happen to the EVM. You have some sort of excitement in the form of a transaction or an entire block with transactions. And then you have the post state. So the post state is from the pre-state, assuming you perform the excitement, what is the view of the world afterwards? And with these kind of free items, and we pass it into the state test field, state test function, which or parameter, which the fill command uses to generate the test fixture. So I can just do that now. So I'm within the repo. The first thing you want to do when you clone the repo is run uv sync. So you need to install uv, but all of this is on our documentation, which is very clearly labeled. It's not too difficult. So assuming uv is installed, which is a Python package manager written in Rust, it's very fast. You then want to run fill. So here, I'm typing uv run fill. I'm using a PyTest marker k to mark the test that I want to run. So this test is called test simple example. So test simple example. Dash v essentially gives you a more verbose overview when filling. And dash m is a PyTest marker. I'm going to mark it to only fill state tests. And I'll show you more about that later. Let me. Okay, we didn't really see that clearly. Oh. Okay, let me do that again. So, okay, so this essentially using the reference EVM transition tool starts filling tests, and you can see that this test has been filled. So the output from this is a folder called fixtures, and within it, it contains the tests that you just generated. So if I open this test, simple example, here is the test that we just generated. I'll go back to test simple and kind of explain what's happening here. So to set up the pre-state for this test, or to give you more context, this is a very simple test. All we're doing is testing that a type 1 transaction does something. And it contains an access list just because why not? So we set up the pre-state and we set up a contract address with some bytecode. So this contract, all it does is it performs an S store. So it stores the value 1 to the index 0. We give it some initial balance of free. We also have a sender, and we fund the sender with this balance. And the sender sends this transaction to the contract address. And then after that's executed, what we want to see is that the contract address contains the bytecode that we set here, the S store. As you can see here, this is a push 1, a push 0, and then an S store. We can validate that the balance changed. So with this transaction, we send a value of 1, hence the balance has changed from 3 to 4. And we're checking that the nonce is incremented. And additionally, the seller balance exists as well. And this was the starting balance. After sending this transaction, this is the balance that we want. And I can just change a few things here to make filling fail. And so let me first of all let me change this balance to free. So now if I run fill again, the checks when filling should fail. Okay. So 1 failed. We look up at the error. Unexpected balance for accounts. Want free, got 4. So because we changed this to free, yeah, this is why the error occurred. Now, typically when we define things in the post state, it specifies what we want to see. Now, if I remove balance here, because we're not trying to assert anything, this should pass. So you can be as specific as you want to be. You could test the balance for everything. So this test should fill. And similar with the nonce, I could remove the nonce. Move the nonce here. But typically, if you want to test something, you have to use an store to store the output of something, typically. So this is just a state test. And we have two main test formats, like I mentioned before. So there's additionally the blockchain test, and you can think of a state test as essentially just running a single transaction to test something very specific in the EVM. And with a blockchain test, you're running maybe multiple blocks and testing interactions between blocks. So what I can do here now is I can remove this here, and we can make this this simple example test a blockchain test. So we're no longer using the state test filler. We use the blockchain test filler. Get the imports back. So again, we have the initial pre-state. We still need to define the transaction because we'll place that in the block in a second. So let me just copy over the code I had previously. So here we've defined block 1, the block object, and inside it, it contains a list of transactions. And this transaction here is a transaction we defined above. And additionally, we can add some extra block fields. So since Shanghai, we added withdrawals. So I've added a random withdrawal here. And we can create a blocks field, which is a list of blocks. Just going to do a single block for now. And then, like we did before with the state test, we can define the blockchain test. Okay, some indents here, which are not making me happy. Okay, now if I want to fill this test, I'll remove the state test marker, and I'll just add the block test marker. Now these typically aren't blockchain test marker. Typically these aren't added, but again, I'll show you in a second why I've added them. So now if I run this, this should create a blockchain test fixture. Okay, it's filled. Now I can open this up. Go to fixtures. Okay, so now we have state tests and blockchain tests. So if we open state test again, you'll see we have some environment, the initial environment, the pre-state. It's worth saying that this environment can be controlled within a test, but typically it's handled automatically by the framework. With the pre-state that we defined in our MPT format, Merkle Patricia tree, we have the transaction that we defined, and then we have a post state that is checked. Now, if we open the blockchain test example, it's a different format. So here we start with a Genesis block header. So when a client consumes this test, this is the block, the Genesis block. And we have the pre-state as well, like before. We have the post-state in the form of a MPT as well. We have some meta fields here. So the last block hash, which is the last block hash of the blockchain, which should be the block hash of this single block. The RLP of the Genesis block. And here we actually have the blocks. So because we only added one block, we have a single block. So here we have the single transaction within the block that we added, and the withdrawals that we added as well. Just block one. And if we just check, this is the hash, so 08103 of the block, and it matches the last block hash. Now what we can also do, we can add multiple blocks. I can add just dummy blocks here if I want to, just an empty block. We've added 3. I'm going to refill the test. And now this blockchain test should have 3 blocks. So it's filled. Okay, so here we have the same block as before, block 1, then we have the second block, just a dummy block, with no transactions, no withdrawals. Third block, again with no transactions and no withdrawals. So hopefully this gives you an overview of writing some simple tests in 2 different formats, the state test format and the blockchain test format. And one other thing I can show you, just some cool ways that you can use fill. So let me go back and remove the blockchain test format, and we will get this as a state test again. So I'm just going to undo everything I did. Okay. Now, if I remove the marker, firstly, actually, let me remove the fixtures that I generated, so we have fresh fixtures. Okay. So now fixture should not exist. It does not exist. If I run this again, nope. No marker. So now we're not marking for a specific type of test. And you'll see that we fill 3 different types of tests from a state test. Now, what the framework does is that for every state test, assuming you don't mark it in a way that it can't be generated as a blockchain test, for every state test, it generates it as a blockchain test. Now, this allows us to essentially test single transactions as state tests within blocks as well, within the blockchain test format. It gives us more for one test. And the reason we can do that is if we have the transaction, we can just place it in a block, right? Now, additionally, for blockchain tests, they're also generated as an engine test format. And essentially what this is instead of generating the blocks, we generate the engine new payloads or the execution payloads. So, and we use this to test the engine API. So we have the free test, the state test that we had before, the same blockchain test that we had before, the initial one, and now the blockchain engine test. Now if we go in here, it should look exactly the same, but instead of having the blocks, we have the engine new payloads. So again, this helps us test clients in a kind of more realistic manner, realistic view, considering that this is how execution layers actually executes blocks, right? It gets the engine new payloads. Okay, now I think that's a good overview of generating the tests. One thing I can also do, so let me mark this valid from, let's do Shanghai. Okay, now if I fill this again, this should generate the tests for the Shanghai fork and also Cancun. Now within Shanghai, we added withdrawals. Within Cancun, we added blobs. So if we go back to the fixtures, within the test, there should be 2. So here we have the state test for the Shanghai network. So it has the withdrawals. Again, the withdrawals. And if we go to the Cancun side, it has the blob gas. And similarly for the state tests. So Okay. So what else can I show you? So I guess the reason I wanted to show you that is if you find a bug and you write a test for it, marking it from the latest fork, right? So Cancun. How do you know what fork the bug started at, right? So if you really want to check, what you can do is assuming the test you write is valid for a specific fork. For example, if you try and add withdrawals to Paris, the test won't fill because withdrawals aren't added to Paris. So assuming your test is a valid test, and that the test is correct for the fork you're filling for, you can see, or you'll be able to determine the fork that a bug started from. Now, this isn't super important, but it can definitely give you more context and help you kind of navigate and help teams navigate how to actually fix the bug. Okay, so let me go back to presentation. So hopefully this gives an overview of how writing a test and filling the actual test to a JSON fixture works. The next step here is consuming the test on a client. So how does a client actually use these JSON fixtures that we've generated and consume them to run the test? So for this, we have consume. Now there's 3 different ways of running consume. For now, I'm going to go over consume direct, which is a kind of local way of testing. So consume direct, what it does is it gets the fixtures that we generated, and it wraps around a client interface. So for example, Geth have a state test and a block test command within their EVM binary that you generate. So it's a command that Geth uses internally to actually run these tests. And other clients have similar commands too. And what consume direct does is it essentially wraps around it and checks the errors. For example, if we have an invalid test, and what it does, for example, like the test expects a specific type of exception, consume direct reads the exception from Geth and maps it to the error that we've assigned it in the test to make sure that the invalidation is correct, right? And yeah, essentially, once it's done, it generates a test report, or as you can see in the terminal, it will say if the test is passed or failed. So what I can do for that, so here I'm just in Geth, so I've just cloned Geth and I've created a separate branch for today. It should be exactly the same as master. And what I can do is I can run make all, which makes all the binaries within Geth, but the binary that we actually want to make is the EVM binary. Now I can just cancel this because I've already done it. But what you'll see is that I have this EVM binary already in my path. So EVM block test, and you can pass it the test fixture to run it. So this is typically how Geth would run it natively themselves. If I go back here, so that matches the commands here. So now that we've built that within Geth, what we can do back on the Execution Spec Test repo. Let me. Oh, I've lost the terminal. What am I doing? There we go. And what we can do is we can run consume direct. So consume direct, we point the EVM binary that we just made on Geth for consume direct, and we pass it the fixtures that we just generated. Now the expectation here is that running this, Geth should pass, and it did. You can see it clearly when I lower the font, but it passed the blockchain test and the state test. You'll notice it didn't run the engine tests. That's because those have to be run specifically within Hive using a different type of consume command. But yeah, this is how we can execute the generated test locally very fast. Now, unfortunately, consume direct right now is only working for Geth. So I will show you different ways to run the tests, not just using consume direct. But quickly, what I want to show you is kind of what it would look like if you found a bug. So let me navigate to a different test. So here we have test blob transactions. Essentially what this test does is it checks that all valid blob combinations pass on a client. So what's a valid blob combination? Well, because EIP 4844 added this max blobs per block field, you can only have a maximum of 6 blob transactions within a block. So this function here, and let me find it, all valid blob combinations here. So it just returns a list of all these combinations, and then that is used within this test here using a PyTest parameterization. I won't go into detail of that. But yeah, so let me generate those tests. So first, I'm going to remove all the fixtures that we generated before. I'm going to run these fixtures. So let's test valid transaction blob combinations. We're going to run it only for Cancun. Okay. Nice. So as you can see, because of the kind of magnitude of combinations, this generates 88 tests. Now, note that this is a blockchain test. So we're not generating any state tests here. State tests can generate a blockchain test. Blockchain tests can only generate the blockchain tests and the blockchain engine test. So here we have 44 tests for the typical basic blockchain test fixtures, and the same for engine fixtures. Now within here, this will just be a list of all of these. So a lot of tests in here. But now what I can do is I can run these fixtures on Geth again. So let me do that. Okay, and as you'd expect, I'm running the blockchain tests. They're all passing right now. Okay, now what I can do is I can go into Geth. So let me open the terminal again. So I can open Geth. Okay, and I can try and create a bug within Geth. So a very simple bug. So essentially all I'm going to do here, so here there are some parameters that are defined and used within Geth. I'm going to change this field, the max blob gas per block, to be 5 times the blob transaction blob gas per block. So this essentially means 6 blobs right now, because the maximum is 6. But what I can do is I can say that it's that the maximum is 5. So now if I do that, I can remake the Geth binary to essentially update it with this bug I've created. So we'll wait for that to happen. Yeah, let's wait still. Okay, it's done. Now if I go back to Execution Spec Tests, now if I run this, any of the valid block combinations here, so any that are have over 5, should fail. So let's just run this. So we should get some passes and some fails. Okay, it wasn't very clear there, but we did get some fails when consuming these fixtures. So let me remove the verbosity. Here you can see it does it very fast. Oh my, am I going to keep scrolling forever? I'm not. Essentially, some passed, some failed, and this is the failure here. So running the generated test fixtures, and we get this error, bad block on the first block that exists in the test. Blob gas used, this number exceeds the maximum allowance. And that's because we lowered the maximum allowance to be 5 times whatever the constant was instead of 6, right? So this, in reality, should be this number here on Geth. And yeah, I can reopen Geth again. And we can go to that exact error. So this is where the error is triggered here. So because the blob gas used exceeds the max that is defined because we lowered it, and we trigger this error. This number exceeds this number. Now, this is a very simple, if this was a bug, it's extremely simple, right? Realistically, this isn't, you're never going to find something like this. It'll be way more complex. But hopefully this gives an overview now of, okay, you've written a test, you've generated the test fixture JSON file, and now you've consumed it against the client. Okay, so consume direct is one way of consuming a test. So let me open up slides again. So we have two other methods, consume RLP and consume engine. Here is consume RLP. Now, this differs because it uses Hive as a kind of a back-end environment. Now, it also differs because instead of running the test locally, you're first within Hive launching a fully instantiated client and then running the tests. So with consume RLP within Hive, what this does is it uses the blockchain test fixtures that we've generated. The RLP encoded, the block RLP within those tests is used and loaded within the client on startup, so that as soon as the client starts, it starts executing all the blocks. And essentially, within Hive, this is what we do, and we once it's executed all the blocks, we verify if it's the last block hash after executing everything is correct. Now again, this uses Hive, and so I can quickly go over what Hive is. So Ethereum/Hive is essentially just a test harness. It allows us to spin up clients in Docker containers, fully instantiated client, have a simulator in a separate Docker container where Hive kind of controls the interaction between them. This diagram should hopefully explain it a bit better. So you have your simulator, your test simulator. In our case, it's going to be consume RLP. And then Docker kind of using these APIs internally into Hive will spin up a client based on what we've defined in the simulator. And then these interactions will happen, and then we'll get the results back. Just a very brief overview. And again, there's another simulator, consume engine, but for now, we're going to go back to consume RLP. So consume RLP and consume engine are run in Hive. So let me just open up Hive. So this is the Hive repo, Ethereum/Hive. And within it, what we can do is we can run specific simulators. So there is other methods to run this locally, but I'm going to give you the generic overview of Hive and how Hive is typically ran. So here we're running /Hive, which is the Hive runner. We're pointing the simulator we want to run, the consume RLP simulator, the client we want to run it for, and here we're stating Docker to output logs. So if I just back up for a second, now we can go into these simulators. So within the simulators, because everything is running within or is using our repository, what we've done is essentially the simulator is just a Docker file which clones our repo, installs everything it needs, and then runs the consume RLP command from within our repo clone within the Docker container. Now here, I've pointed it to some fixtures that that I've already created. And these fixtures have already been created using, these are the same fixtures that we just generated for the blob transactions, the valid blob transactions. So I can go back here. So these fixtures here, the fixtures that I've pointed to within the Docker file are these exact same fixtures. Okay, so when we run Hive like this, and we run that Docker file essentially as the simulator. Now, if I run this just with geth consume RLP, the expectation is that everything should pass. And if we run it, everything should pass right now because we are running these tests on geth's master branch, not the branch that we created with the bug. So we'll just wait for that to keep running. And on our geth side, we will quickly add the bug. So we added the bug here, this line. Let me add that. Oh. I'm going to push it to our branch, Immunefi geth. Okay, so our bug is added to this branch. If we go back to Hive, okay, all the tests, they passed. Okay, 0 failed. Now, the reason that is because we've just defined the client as Go Ethereum. We've not defined any specific branch that we're running on. So this will just run on master. So what we can do is we can add something called the client file flag, pointing that to this folder called configs, and a file that we created earlier called immunefi.yaml. Before we run that, let me just open it up for you. So here is what this config file looks like. We define the client, some arbitrary name, the type of Docker file build we're going to run. So because we're using Git, specific Git tags, we define that as Git, and the build arg. So here we're pointing to my fork of geth and the branch that I created, the branch I just pushed to. Okay, so if we now run this, hopefully this should spawn the errors using the consume RLP simulator. Okay, this should run fairly fast. Nice. A few more. Okay, now 18 failed. So the same as before, but all we have is a block hash mismatch. So it's not precise, but it tells us that there's an error, right? Based on the test. The reason that is, as I said before, is for the consume RLP simulator, we load the block RLP, or we load the client up with block RLP, and the client just executes all the blocks. Then at the end, we fetch what the last block hash is, and we compare it with the expected last block hash. And this is the mismatch here. So now we've covered running consume direct locally, consume RLP in Hive. We can do the same with consume engine. And essentially this is different because it will, instead of loading the blocks up on startup, the client is loaded up initially with the Genesis block, and then we send the blockchain engine fixture new payloads one by one. So if there's multiple blocks, we send them one by one. If there's one block, we just send one. And the response is different here. So this is testing a different entry point. So the way I like to think about it is the consume RLP kind of tests like a block syncing. An engine is more realistic, like a more realistic mainnet type test. So I feel like this gives us the best test using the engine API, in my opinion. And as you'll see, we expected a valid payload, but we got an invalid payload. And the error is the same as before. Blob gas used exceeds the maximum allowance. Okay. So that was consume RLP, and also consume engine. Now, hopefully that made sense. I did go over that very quickly. There are other ways to run Hive, but again, for the sake of this presentation, this was the way I kind of wanted to show it. You can run Hive in something called developer mode. So if I do /hive --dev, and essentially here I could go Ethereum, and this starts this Hive proxy, and it waits for an external command or external notification to come from somewhere else. And assuming it gets this notification, the Hive proxy will handle it and essentially start up a client. So if you wanted to run this locally, you can use Hive Dev mode. This only works on Linux right now very natively, but essentially it allows you to run consume RLP from within locally, like you did run consume direct, and that you locally send something to this Hive Dev mode here, and then Hive will run the simulation for you. This differs to what we've done now because we're running everything within Hive. We're calling the repo, the execution spec test repo, and then running it directly within everything within Hive. But we can do it slightly faster if we run it locally. But again, I won't go into too much detail on that. One thing that's worth mentioning is that, again, consume direct right now only works for Geth. So if you did want to run tests for other clients, execution of their clients at Bezier, you'd want to be running consume. Where did consume RLP go? Yeah, consume RLP or consume engine, like I just showed you. Yeah, I think that's about it from what I wanted to go over. I feel like given the amount of time, it's hard to go over everything, but hopefully that gives a reasonable overview for you to look into more detail, into some documentation. So this is our main execution spec test documentation. It is very thorough. It's very well written. So yeah, if you want to look at that, it's there. And this is the Hive documentation, just on the Hive repo. Gives you more understanding about Hive. And if you want to look into any more of this, DevCon just happened. So Dan, who's in the call now, just did a presentation on EEST in a bit more detail, of the history. So if you want to learn more, that's a really good place to go. So this points to a YouTube video. And similarly with we organized a workshop where Mario kind of went over the execute command, which I mentioned earlier, called Hunt the Bug, Save the Chain. And again, the execute command sends Python tests to a live network. So this was more for development, I guess. But if you're intrigued to learn more about what a repo does, you can also watch that video here. It's about an hour and a half, I believe. So yeah, I think that's about it. If there's any questions that we could go over, if there's anything that didn't make sense, I'd be happy to answer some. And Dan, if there's anything you wanted to add, if I made any misjudgments, feel free to to speak up.
I think this was an amazing presentation. Thank you, Spencer, so much. No questions for me for sure. Thank you for hosting this and essentially leading it. Guys, I think we can wrap up here. So thank you so much for your time. I'm gonna stop the recording.